Not all tank armor designs of World War II succeeded. While history often highlights legendary vehicles and effective protection systems, many armor concepts failed under the realities of combat. These failures were not always the result of incompetence. In most cases, they reflected flawed assumptions, industrial limitations, outdated doctrine, or an inability to adapt quickly enough to changing battlefield conditions. Understanding failed tank armor designs offers a clearer picture of how armored warfare truly evolved during the conflict. At the beginning of the war, many nations entered combat with armor philosophies rooted in interwar thinking. Tank armor was often designed to resist threats that were already becoming obsolete. Early armor designs assumed limited anti-tank firepower, short engagement distances, and slow-paced maneuver warfare. These assumptions collapsed rapidly once modern anti-tank guns and combined arms tactics were introduced. One common failure across multiple nations was excessive reliance on vertical armor plates. Flat, unsloped armor reduced manufacturing complexity but provided poor ballistic efficiency. Even relatively thick plates could be penetrated by high-velocity rounds at moderate distances. As a result, tanks with vertical armor surfaces suffered higher penetration rates than designers had anticipated. This flaw became especially apparent when compared to later designs that used sloped armor to increase effective thickness. Riveted armor represented another widespread failure. While rivets simplified production, they created a dangerous internal hazard. When struck by enemy fire, rivets could shear off and ricochet inside the fighting compartment, injuring or killing crew members even without full penetration. Many early war tanks relied heavily on riveted construction, only for crews to discover that armor meant to protect them could become a source of lethal fragmentation. Thin armor used in the pursuit of speed also proved to be a costly mistake. Several nations prioritized fast tanks with minimal protection, believing mobility alone would ensure survival. In practice, speed offered limited protection once tanks were detected and engaged. Thin armor left crews vulnerable to even light anti-tank weapons, heavy machine guns, and artillery fragments. These designs failed not because mobility was useless, but because it was treated as a substitute for protection rather than a complement. Another major failure involved underestimating the pace of anti-tank weapon development. Armor designs that were adequate at the start of the war became obsolete within a few years. Tanks that could resist early 37mm or 40mm guns were quickly rendered vulnerable by larger calibers and improved ammunition. Designs that lacked growth potential or upgrade capacity were especially prone to failure, as they could not adapt to evolving threats. Doctrinal rigidity also contributed significantly to armor failure. Some armies designed tanks for highly specific roles, such as infantry support or exploitation, without considering how rapidly battlefield conditions might change. Armor optimized for one scenario often performed poorly in others. Tanks designed to support infantry at slow speeds struggled in fluid maneuver warfare, while lightly armored reconnaissance vehicles were often pressed into roles they were never meant to fulfill. Industrial limitations compounded these problems. Nations with restricted manufacturing capacity often compromised armor quality, thickness or heat treatment to meet production demands. Inconsistent armor hardness, poor welding techniques, and uneven plate quality reduced real-world protection. On paper, armor specifications appeared adequate, but battlefield performance told a different story. Several tank designs also failed due to poor armor layout rather than thickness. Vulnerable weak points such as thin side plates, exposed vision ports, or poorly protected turrets allowed enemy gunners to exploit predictable penetration zones. Even tanks with reasonably thick frontal armor could be disabled or destroyed by shots to less protected areas. The absence of sloped armor in many early designs represented a missed opportunity. Sloping increased effective thickness without adding weight, improved ricochet probability, and enhanced overall survivability. Nations that failed to adopt sloped armor early paid a heavy price in vehicle losses and crew casualties. This failure was not due to ignorance, but to conservatism and manufacturing inertia. Armor failure was also influenced by unrealistic testing environments. Pre-war trials often failed to replicate real combat conditions. Armor was tested against outdated weapons, at controlled angles, and under ideal circumstances. Once exposed to modern anti-tank fire, these designs revealed vulnerabilities that had not been anticipated. Combat became the ultimate proving ground, and many armor concepts failed that test. Crew feedback frequently highlighted the shortcomings of failed armor designs. Reports described armor cracking, spalling, and catastrophic penetration even at ranges designers believed were safe. These experiences forced armies to reassess assumptions and revise future designs. Unfortunately, such lessons were often learned at great cost. The psychological impact of inadequate armor should not be overlooked. Crews who lacked confidence in their vehicle's protection were more cautious, less aggressive, and more prone to hesitation under fire. Failed armor designs did not only result in physical losses, but also undermined morale and operational effectiveness. Despite these failures, they played a crucial role in advancing armored warfare. Each flawed design provided valuable lessons that informed subsequent improvements. Sloped armor, better welding techniques, increased thickness in critical areas, and improved internal layout all emerged as responses to earlier failures. Failed armor designs also demonstrated that no single solution guaranteed survivability. Armor had to evolve alongside tactics, weapons, and operational doctrine. Designs that treated armor as a static solution inevitably fell behind. Adaptability became the defining factor in successful tank protection. By the midpoint of the war, many early armor failures had been recognized and corrected. However, the tanks that carried those flawed designs had already seen combat, often with devastating consequences. Their legacy lies not in success, but in the lessons they forced engineers and commanders to learn. Understanding failed tank armor designs offers a more honest view of World War II armored warfare. Victory was not achieved through flawless engineering, but through continuous correction of mistakes. Armor that failed helped shape armor that succeeded. These failures remind us that technology does not evolve in isolation. It reflects assumptions, resources, and the urgency of the moment. World War II tank armor failures were the product of a world learning how to fight a new kind of war in real time. This perspective sets the stage for a deeper examination of specific national failures, design errors, and battlefield consequences. Each example reveals how even well-intentioned armor concepts could collapse when confronted with modern warfare. The story of failed tank armor is therefore not one of incompetence, but of adaptation forged through necessity and sacrifice. As the war progressed, the failures of tank armor designs became increasingly visible across all major combatant nations. These failures were often the result of decisions made years earlier, before the true nature of modern armored warfare was fully understood. Japanese tank armor failures followed a similar pattern. Designed primarily for infantry support and operations in Asia, Japanese tanks featured thin armor that proved insufficient against Allied anti-tank weapons. When Japanese tanks encountered American armor in the Pacific, their protection was quickly overwhelmed. Armor that was adequate for one theater failed catastrophically in another. Soviet armor failures are often overshadowed by the success of the T-34. However, early Soviet designs suffered from poor armor quality, inconsistent heat treatment, and inadequate internal layout. Thin side armor and weak welds created vulnerabilities that enemy gunners exploited. Even tanks with sloped armor could fail if construction quality was inconsistent. American tank armor failures reflected a different set of priorities. Early U.S. tanks emphasized reliability and production speed over maximum protection. Vertical armor plates and relatively thin frontal protection left some vehicles vulnerable to German anti-tank guns. While these designs supported mass deployment, they also demonstrated the risks of prioritizing quantity over survivability. Across all nations, one recurring failure was the inability to anticipate the rapid escalation of firepower. Armor that was sufficient one year could be obsolete the next. Designs that lacked upgrade potential became liabilities, forcing armies to field vehicles that crews knew were vulnerable. This technological lag proved costly in both material and human terms. Another critical failure involved the underestimation of side and rear armor vulnerability. Many tanks featured thick frontal plates but neglected lateral protection. Enemy forces quickly learned to exploit these weaknesses through flanking tactics and ambushes. Armor that protected only one direction failed in the dynamic environment of mobile warfare. The human cost of failed armor designs was severe. Crews faced increased risk of penetration, spalling, and catastrophic explosions. Reports from the field consistently highlighted the dangers posed by poorly designed armor. These experiences influenced morale, tactics, and the willingness of crews to engage aggressively. World War II tank armor failures illustrate how engineering, doctrine, and industrial capacity intersect under pressure. This broader understanding sets the foundation for examining how these failures influenced post-war tank design. The mistakes of World War II were not forgotten. They became the blueprint for future improvements. Armor that failed helped define armor that would succeed. The story of failed tank armor is therefore inseparable from the story of progress. Each weakness revealed a path forward, and each loss reshaped the next generation of armored vehicles. These failures, while costly, were instrumental in transforming armored warfare. In examining these designs, we gain a clearer picture of how modern tank protection evolved. The failures of World War II were not anomalies, but essential steps in a larger process of technological refinement. They reveal the realities of innovation under fire and the price paid for mistakes. As this examination continues, it becomes clear that no nation entered the war with perfect answers. Armor failures were universal, reflecting the unprecedented challenges of modern warfare. Understanding these failures provides valuable insight into the complexity of armored combat and the necessity of continuous adaptation. When the full scope of World War II is considered, failed tank armor designs emerge not as isolated mistakes, but as symptoms of a global learning process under extreme pressure. By the final years of the war, nearly every major combatant had identified the flaws that plagued early armor concepts. The contrast between early failures and later improvements reveals how rapidly armored warfare evolved once battlefield realities replaced pre-war assumptions. One of the most definitive lessons was the rejection of armor thickness as a standalone solution. Tanks that relied solely on thicker plates without addressing layout, slope, and internal safety consistently underperformed. Heavy armor, increased weight, reduced mobility, and strained mechanical systems without guaranteeing protection. These designs failed because they misunderstood the nature of survivability, which depended on probability, not absolutes. Another critical failure involved the misconception that frontal armor alone defined protection. Early tank designs often emphasized the frontal arc while neglecting sides, rear, roof, and underbelly protection. Combat experience proved that threats emerged from all directions. Mines, artillery airbursts flanking anti-tank fire, and close-range infantry weapons exposed the inadequacy of unbalanced armor schemes. Tanks that failed to protect crews comprehensively were at a severe disadvantage. The failure of riveted armor became universally acknowledged by mid-war. While rivets had simplified early production, their lethal internal effects could not be ignored. The transition to welded armor marked a turning point in crew survivability. Tanks that retained riveted construction suffered disproportionately, confirming that internal safety was as critical as external resistance. This realization reshaped armor engineering permanently. Inconsistent armor quality also emerged as a decisive factor in failure. Variations in steel composition, heat treatment, and welding quality produced armor that behaved unpredictably under fire. Two tanks with identical nominal armor thickness could perform very differently in combat. This inconsistency undermined crew confidence and complicated tactical planning. Reliable armor, even if thinner, proved more valuable than thicker armor of questionable quality. Doctrinal inflexibility compounded technical failures. Tanks designed for narrow tactical roles often found themselves misused when battlefield conditions shifted. Armor optimized for slow infantry support was vulnerable in maneuver warfare, while lightly armored reconnaissance vehicles were destroyed when pressed into frontline combat. Designs that failed to anticipate role expansion paid the price in losses and inefficiency. While not perfect, later designs demonstrated a more realistic understanding of battlefield threats. Armor no longer promised invulnerability, but survivability through probability, coordination, and adaptability. This philosophical shift marked the true end of early war armor failures. Post-war tank development was profoundly shaped by the mistakes of World War II. Engineers analyzed penetration data, crew reports, and battlefield damage to refine future designs. The failures of riveted armor, vertical plates, and unbalanced layouts became foundational lessons. Modern armored vehicles are, in many ways, a direct response to these wartime shortcomings. Importantly, failed armor designs were not purely the result of poor engineering. They reflected economic constraints, political urgency, and the need to field vehicles quickly. In many cases, designers understood the limitations but lacked the resources or time to implement better solutions. Failure was often a compromise imposed by circumstance rather than ignorance. World War II demonstrated that armored warfare evolves faster than doctrine. Armor designs that failed did so because they were overtaken by events. Firepower advanced more rapidly than protection, forcing continuous reassessment. Tanks that could not keep pace with this evolution were exposed mercilessly on the battlefield. The study of failed tank armor designs provides a more honest narrative of the war. Victory was not achieved through flawless machines, but through relentless adaptation. Each failed design contributed data, experience, and urgency that shaped subsequent improvements. Progress was forged through loss. These failures also underscore the human cost of technological misjudgment. Behind every flawed armor plate were crews who faced unnecessary risk. Their experiences informed changes that saved lives later in the war. In this sense, failed armor designs played a tragic but essential role in advancing survivability. They marked the boundary between old assumptions and modern armored warfare. Their shortcomings illuminated the path forward, shaping how tanks would be designed, built, and employed for generations to come. World War II tank armor failures were not merely technical shortcomings, they were the growing pains of a new era of warfare. Through trial, error, and sacrifice, armored forces learned what protection truly meant. In that process, failure became the foundation of progress. This understanding brings clarity to the evolution of armored warfare. The tanks that failed mattered as much as those that succeeded. They revealed the cost of miscalculation and the value of adaptation. In the end, their legacy is written not in steel thickness, but in lessons learned under fire.